Hi, this is part two dealing with nuclear binding energy, and I probably should write the word nuclear up here. Remember, nuclear binding energy is analogous to ionization energy, except it's a whole lot stronger. Whereas ionization energy is the amount of energy needed to knock an electron out of an atom, electron cloud, so that the atom becomes positively charged, becomes a positive ion. Nuclear binding energy is the amount of energy needed to break an intact nucleus up into its separated protons and neutrons. So we learned that. But there's an application now that we can deal with in terms of nuclear reactions. Okay, so let's take a look at this particular example. So example number one of a nuclear reaction. Let's say we have polonium 210, the isotope polonium 210, and it undergoes nuclear decay. It undergoes natural transmutation, and let's say that it converts to a lead 206 nucleus. What else do you think it would be produced here? Can you figure out what this other product's going to be based on what we have so far? Well, 206 plus what gives us 210? And the answer is 206 plus 4. So remember, the masses on the right-hand side of this nuclear equation have to add up to the same amount of mass on the left-hand side. And the charges also have to be conserved. So if we have 82 positive charges over here, 82 plus what gives us 84? And that would be 2. So this is the identifying feature for an alpha particle, or a helium nucleus right there. This alpha particle would zoom off really fast, probably, right? Because of energy being released. At least that's what we're assuming. Let's see if there's energy being released. Let's see if this thing is an exothermic nuclear reaction. Okay? So what we can do is use our binding energy concepts and kind of modify it a little bit. So this time what we'll do is we'll look up the atomic mass for polonium 210 in a table, and it turns out it's 209 point, and I'll just write it out instead of saying it out loud. This many atomic mass units for polonium 210. And let's do the same thing for lead 206 on the other side. Remember, this is the reactant side. These two things are the products. So let's look at the product side. Let's look at lead 206, and we look up its mass in the table. That's 205 point, and then I'll just write it out. In terms of helium, okay, we look that up, and that is 4.00260 atomic mass units. Okay, now let's add up the mass of the products. If we add those two masses up, we get 209.977 atomic mass units. So this is the mass of the products of the nuclear reaction. And then the polonium, we already know the mass of the reactant. Okay, so we have the mass of the reactant, mass of the product. Let's compare the sizes. Okay, so here's the mass of the reactant. Here's the mass of the two products combined. Hey, look, we see that the mass of the reactant is bigger than the mass of the products. So what does that mean? Well, since this nuclear reaction actually lost mass in forming products, that must mean that it released energy. And so my hypothesis about releasing a fast alpha particle is correct. Okay, a lot of kinetic energy released because this reaction lost mass in converting from reactants to products. And if it lost mass, that must have mean it released energy, and so this reaction is an exothermic reaction. Did you get the reasoning behind that? It's an exothermic reaction because we can see that the mass of the products is less than the mass of the reactant, and that difference in mass must have been released as energy. Okay, and in this case, it was enough energy to take that alpha particle and shoot it off away from the lead nucleus at a very fast speed. Okay. All right, so that's the idea. So this is kind of a modification of dealing with nuclear binding energy, isn't it? We're just taking the mass of the reactant, comparing it with the mass of the products, and if we subtract, we're going to be able to find out how much energy is released. So let's go ahead and subtract those two now. So we'll take 209.982 units minus 209.977 units. And that difference in mass is 0.0054. That's supposed to be a 4 units. So that's the mass difference. I'll call that delta M now. Now remember what we can do. We can take and find the energy in mega electron volts by taking our mass in atomic mass difference in atomic mass units and multiplying it by the conversion factor of 931.5 mega electron volts per atomic mass unit. And again, the little u's cancel out, and that leaves us with mega electron volts. 5.447 mega electron volts to be exact. So this is the energy released during this nuclear reaction. What kind of reaction is this again? This is alpha decay, right? This is an alpha decay reaction because it produced an alpha particle. Okay, so that's example one. That shows how we can actually deal with how much energy is released during a nuclear reaction. And we can tell if it's going to be released energy, exothermic, or if this side happened to have more mass than the reactant side, that would indicate that it would be an endothermic reaction. All right. Okay, now what I'd like to do is have you look at a graph here. In fact, yeah, that's good. We can look at this graph. And this is a graph of binding energy per nucleon. Binding energy per nucleon. And it's in terms of mega electron volts per nucleon. And then on the x-axis we have our mass numbers, the numbers of protons plus neutrons. Okay? So this is protons plus neutrons. And if we look at this graph, it looks pretty strange right now and not very comfortable, but this little peak, we would have different isotopes of hydrogen and helium, and then we get to that peak there, and that peak represents the mass. I mean that represents helium right there. So this is helium, and then we keep getting bigger and bigger in terms of mass number, and eventually we get to the point where we have well, it'd be actually here. The peak, it'd be around here. It would be the mass of iron and the mass of nickel and those kinds of elements. And then when you get over to here, we get to the point where we're getting to really big nuclei. Let's see, 200 and more. Well, that'd be like polonium, lead. So we'd have lead 206, if you recall that, polonium 210, and we would get to uranium 235 and so forth right there. So polonium 210, lead 206. So the real big radioactive elements would be over here. But the peak of this graph would be where we have our iron and our nickel and those kinds of things. And then over here on the far left, we have our small elements like hydrogen, helium, lithium, and so forth. Okay? How do we interpret this and how do we use it? Well, binding energy itself per nucleon, that's how much energy is needed to break that atom apart. Okay. If we look at the peak here where we have iron and nickel, they have the most they require the most binding energy per nucleon. They require the most. That means they're the most stable nuclei. Are up here, the most stable nuclei, because they require the most binding energy, the most energy to knock those nuclei apart. Over here, as you get to bigger and bigger elements, those bigger and bigger elements, which happen to be more naturally radioactive, they don't require as much binding energy, do they, in order to break them apart? So that's interesting. And then on the smaller part of the periodic table, we have elements that don't require as much binding energy to knock them apart either, except for helium, helium-4, which happens to be very stable also. But you know, hydrogen, lithium, and all these, they don't require as much energy to knock them apart. So there's something about the small nuclei over here versus the big nuclei over here, which makes them less stable. But then something about the iron and the nickel which makes them more stable. Okay, let's look at a variety of different forms of this graph. Okay, and I just kind of I went on Google and got some Google images here. Okay, here we can see our lighter elements. Here's an iron, very stable. Nickel is probably the most stable. That's why we have so much iron and nickel in nature, because it's the most stable. Then as we get to the heavier elements, they would be over in this part. Okay. All right. Now this diagram here is just an inverted picture of the one I showed before. We have these things upside down here. So this is basically just a flip version of that. And the reason that sometimes scientists flip that graph, that first graph here, is to basically show that where it used to be the peak here, now it's a valley. This is more like of a showing the potential energy that that iron has. Iron is lowest in potential energy, and that means most stable. Okay, all the other elements, they're going to try to get down to that potential energy well also, that depression down there. And so if you have heavy radioactive elements, they would tend to radioactively decay and undergo nuclear reactions until eventually their products get to this nice low potential energy state. And the smaller elements smaller than iron and nickel, they would also tend to undergo nuclear reactions until their products would get to that nice low potential energy state. Okay, here's another view of it right here. Potential energy on the y-axis and mass number in terms of protons and neutrons, the number of nucleons along the x-axis. Okay? We'll get back to this in a little bit. Now let's try another example of a calculation. This time an example where we have a nuclear reaction where there's a big nucleus like uranium. So here's an example of what's called nuclear fission. Fission means to split apart. Just one example. There are many examples. Let's say we have a nucleus of uranium-235 and we hit it with a well-placed neutron, and that neutron causes that uranium-235 nucleus to split or to undergo fission. Okay, well, one example of a set of products would be we'd have barium-141 and krypton-92, and you'd also get 3 neutrons that would be flying off, hopefully. Okay. All right, so how do we find the amount of energy? Is this reaction exothermic? Well, let's see. Okay, so we'll just look up in our table what the mass of these things would be. So uranium, I'll just write them down real quick. Mass units and 1 neutron. Okay, so we'd have to add those up, and when we add those up on the reactant side, we get this. Okay, so these are the reactants. It's a reactant side. Okay, now on the product side, we have 3 things. We have barium-141, so that has a mass of 140.910 units. And then we have krypton, which has a mass of 91.92620 units. And then we have 3 neutrons at 1.00866 times 3, so that'd be 3.025994712 units. Add those products up, and we get 235.8628457 atomic mass units. So this is the product side. Now, if we notice that the product side has less mass than the reactant side. How much less? Well, we're going to need to find out, right? So let's go ahead and find the difference in mass. And if it has less mass than the reactant side, that must mean that that lost mass is going to be converted to energy. It's going to release energy, and so this is going to be an exothermic reaction. So we've answered that part of the question. Yes, it is exothermic, and now let's find how much energy will be released. So we'll just go ahead and take our 236.0525889 units for our products minus 235.8628457 units, and I'll just go ahead and subtract there. So minus and we we get the difference would be 0.1897432 units. And now we can convert that to energy by multiplying by 931.5 megaelectron volts per unit. The U's cancel out, so I'll just go ahead now and multiply by 931.5. And we get 176.75 approximately mega electron volts of energy released. That's just for that one nucleus of uranium, by one nucleus of uranium-235. Okay, so that's quite a bit of energy. So uranium-235 has a lot of potential. In this reaction here, when it undergoes nuclear fission, it has a lot of potential to release energy. So this is exothermic reaction. There's a lot of energy being given off, and that's why uranium is used in nuclear power plants and nuclear weapons and so forth. So here's an example of nuclear fission and how to do the calculations. Now let's look back at this binding energy graph. Okay, we see that uranium would be over here, uranium-235, and if I look at barium and krypton, barium and krypton would be much closer in, wouldn't it? Okay. So barium only has like 130, 140. So that would be like right here for barium. And krypton's only at 92, so krypton would be here. So notice that the uranium-235, it had a tendency to undergo fission, didn't it, where it would break apart into smaller isotopes, less massive isotopes. And that's the general pattern. When you look at one of these binding energy graphs and you have an element way over here on the far right, okay, it's going to tend to undergo fission, where it's going to split apart into smaller pieces. Okay? On the other hand, if you have elements like hydrogen over here, or helium, or some smaller elements, when they undergo a nuclear reaction, they're going to tend to undergo fusion, where those smaller pieces would add together to form a bigger piece, which gets us closer to this stable arrangement here that iron and nickel has. So big radioactive elements tend to undergo fission or split into smaller elements, which tends to get closer to this stable region. And smaller elements like hydrogen, helium, lithium, and so on, they tend to undergo fusion, where the product would become more like iron and nickel in stability. Okay? If you have the patience, we can try a last example. This time, let's do an example with fusion, an example of nuclear fusion. Okay, so here's an example of fusion. Okay, let's say we have a hydrogen 2 nucleus colliding with another hydrogen 2 nucleus. Okay, those are the reactants. The products, let's say, happen to, in this case, to be hydrogen 3, or tritium, and a regular old hydrogen 1, our normal hydrogen atom. So here we have two deuterium atoms reacting together, colliding together to form one tritium atom and one normal hydrogen atom. So is this going to be exothermic or endothermic? Let's see. Well, let's look up the masses of these things. The mass of a hydrogen 2 atom is 2.0140. We have two of them. So I'll multiply by 2, and we get for both of them together 4.028 atomic mass units. Let's look over on the product side. The mass of tritium, 3.01605 units, and the mass of a regular hydrogen atom, 1.007825 atomic mass units. If we add those two together, we're going to get 4.023875 atomic mass units. These are the products. Here is the mass of the reactants. Let's compare the masses. Okay, we see that this mass is bigger than, and this is less, therefore mass is lost during the reaction. Therefore, energy is released. If mass is lost, that lost mass must be converted to energy, and that energy is released. Therefore, it's exothermic. Okay? Alright, if we subtract the two to find the mass difference, which I'll just go ahead and subtract this from this, we end up getting 0.004125 atomic mass units for the difference. The energy, then, we can take that difference and multiply it by a conversion factor of 931.5 MeVs per unit, and we get 3.842 mega electron volts released during this nuclear fusion reaction. Fusion meaning that we have these two getting together to form a bigger nucleus. Okay, so if we go back to a binding energy curve, we can see that if we have, let's say, hydrogen 2, which might be here, react with another hydrogen 2 here, two hydrogen 2s here, we're going to get a hydrogen 3 a little higher up, and that would be closer to our stable area up here where we have our iron and nickel isotopes. So hydrogen 2 here, we get two of those fusing together. We're going to end up with a hydrogen 3 here, which is more stable. Okay? Hydrogen 3 is more stable. If we look at it in an inverted graph, okay, we see that the hydrogen 2 fusing together with another hydrogen 2 here would end up forming a hydrogen 3, which is lower on this inverted graph here. It has lower amount of energy, meaning more stable. If something loses energy, becomes more stable, that means it releases. That difference in energy is released. And so fusion, nuclear fusion, is another way to release enormous amounts of energy from a nuclear reaction. Okay, thanks a lot, everybody.